Okay, we're going to be doing 3 lead code questions related to tree traversals. We're going to do them using DFS and recursively and iteratively. So the first one is 144 binary tree pre-order traversal. And for these, I'm not going to use a drawing because they should be self-explanatory in terms of how you view them. So if you have any issues with these, you should just trace them yourself. So given the root of a binary tree, return the pre-order traversal of its nodes, values. So they're going to be back here in our list, right? So this is our tree, right? The root left is null, right is 2, and then left is 3, and that's where it ends. And return 1, 2, 3. The reason why we return 1, 2, 3 is root, left, right. This right here is the root, left, right. So for pre-order traversal is root, then left, then right. All right. So first is the recursive using the first search. So we have an edge case here, which is if root is none, we simply return an empty result. Otherwise, we create a result list, which will store our results. And then we create a function to do the DFS. So we're going to call this function preorder, and it takes a node, right? So this is very simple. You don't need to think about the leaf, the leaves or whatever. You just simply, since we are at the root, you just result.append node.val, and then if node.left is the same as if node.left is not none, right? Or node.left does not equal to none, right? Then we do pre-order node.left. Then again, if node.right, pre-order node.right. Then once we're out of, okay, we just make the function call here. We make a function call, which will be preorder with root, and then here we simply return result. Voila, it works. So this is the recursive condition. So for the iterative condition, what we're going to do is we're going to have a stack, and for each stack we maintain a node and whether it's visited or not. If we find a node that's visited, we iterate through the stack until the stack is empty. And if we find a node that has a visited variable which is set to true, we append that to the result. If it's not set to true, we add that node plus its left and right values, right? So let's do it here. So we create, so now we're going to go for the iterative case. Let me do it like this. Iterative using a stack, right? So edge case remains the same. We create a result, then we instantiate a stack with the root. So stack is equal to root and false, with the root and false visited value, right? So now while stack, in other words, stack is not empty, we pop off the stack. So we'll call this temp is equal to stack.pop, which returns the topmost value. Then we check if the node is empty. So if temp, and we could call it temp or node. Let's call it node. Oh, and then we also need to pop off whether it was visited. So we'll call it visited. We pop off the stack, the node, and its visited value, its visited variable. So if node, this means node does not equal to none, right? Then we check if it is visited. If it is, then we add its result to the result. We add its value to result. We add its value to result. So in other words, if visited, then we simply append the result. So here visited is the same as visited is equal to true, right? Then result dot append node dot val, right? Else visited is equal to false. So what do? We add the node and its children in preorder version. Since we add the node and its children to the stack in preorder version, since it's a stack and we want our value to be added to result to be at the top, we add it using from bottom up. And this, let me show you what I mean. So we know it's root left right, right? So now watch what I'm going to do. Stack.append node, right? And then true, right? So this is our current root, right? Now instead of putting the rest below, I'm putting them on top because I want this to go first, right? So stack.append node dot, so it's root left right, node dot left set to false, stack dot append node dot right set to false. So this will append the children and we'll say the children are not yet visited, right? Okay, so then we return result, because we'll terminate this once the stack is empty, and these will have been added at every single iteration. So when we return, voila, it works. So that's the iterative solution, right? And this is the same one you'll use for all versions of this problem. For example, if it's in order, you'll just change this. If it's post order, you'll just change this, right? So I'm gonna copy some of these notes right here. Okay, so yeah, so that's the solution, and this should take O of n time. The space complexity is O of n for both iterative and recursive solutions. So thank you and bye.